All right, so let's get started. One thing, very quick, I think on the last assignment, I did not look at all of you, but I looked at the first 5 or 6, and I think I agree it was a lot of work, but I don't think anyone really completed all the way to the end. Problem number 2. Did you complete all the way to the end? Somebody here? You did everything? I think so. Okay, so but the majority of the people that I saw did not complete it all the way to the end. So I think I mentioned to the grader just to grade the problem number 1. Okay, I saw some people putting some effort on the second one, but they let go once they needed to start finding the when you need to start going to find the different shear flows by using the stringers. A lot of people gave up over there. Okay, so anyway, now we move really to something that's important about the semester, and this part also might require a lot of work. And I might need a bit of your help out here because I didn't bring my old class notes. So let's see. I should remember some of it. So last week we did what? We did this internal work, or we call about the strain energy, no? And talking about that, we have the strain energy for the different loading conditions. One was the axial. We said that the U strain energy would be equal to 1/2, I guess, was P squared over EA dx, if I remember properly. Okay. All right, this one really, I mean, it doesn't matter. We're going to see that now anyway. So axial, then we look at bending. Bending at the strain energy is 1/2 m squared over EI dx. Okay, these two I'm pretty sure. Then we look at the torsion one, where U will be 1/2. I'm pretty sure that one is T squared over GJ dx, but can you check that one? I'm pretty sure it's that one for torsion. And the last one is really the one I'm going to need help is for shear flow is equal to 1/2, and then we have of what? Of Q over GT ds. Is that correct? Can you check? And then dx. Can you go add for shear flow? What do we have? Should be the last thing we wrote, huh? Or the Q square, yeah, that might be. And then what's dx? I mean, we'll probably go back and find it, but is it dx? Okay. Yeah. Okay. All right. So basically, how can we use all that stuff? Okay. So in order to be able to use all that stuff, is something that is known as the Castigliano's theorem. Okay, so let's say okay, so let's write it. So the internal and external work done can be written in terms of generalized displacement that go with the lowercase q sub I and generalized forces capital Q sub I. Okay, and if you remember, strain energy U is equal to the work done by internal forces. Okay, so basically we're gonna have V internal, which will be equal to the strain energy. We can replace that by 1/2 of stress times strain times dV. And remember, this term over here, okay, is equal to this for axial, is equal to this to bending, is equal to this for torsion, is equal to this for shear flow, no? So that's supposed to be the same term. Now, the work done by external forces, in general, what is work? Work is force times distance, no? Okay, so let's say it would be equal to the summation of all the forces times the virtual displacement, so the generalized forces times the general displacement, and it will be negative because it will be the same thing. The work done, if there's one force pushing down, the internal work is going to try to go in the opposite direction, no? Yeah, so always be negative. All right, so we do all this stuff to define the total potential energy is called capital Pi. Don't ask me why, okay? I could change the notation. I could call it just V total to tell you the truth. But that's the way Castigliano define it. So it should be equal to what? V internal plus V external. So will be equal to U minus the summation of the Q sub of the two Qs. Okay. And basically, this is also known as the theorem of minimum potential energy, but that's what we're going to be doing next. So this will be the total potential energy, on the system. Okay, so just like I said, the principle of minimum potential energy is basically what? How do you find the maximum or the minimum of a function? So basically, if you want to find the maximum in function of one variable, you take the derivative in function of that variable, and you equate it to 0. Perfect. Okay. In this case, I take the partial because what are our two options? We can maximize or minimize this function in function of what? Either the deformation, the generalized deformation, the little lowercase q, or in function of the generalized force, the capital Q, no? We have the choice, no? Okay, so we do that. This is going to give what? Partial lowercase q sub I. I just rewrite the full potential energy, 1 minus the summations, the two q's equal to 0. All right, and this is going to give what? Partial u, partial q, lowercase u, minus the summations of all the forces equal to 0, no? Or this is going to give you that summation of all the forces. I'm going to say this is equal to just the force at that point is equal to the partial of the strain energy divided by the deformation equal to I. Okay, so this one, we don't use this one much at all. But if you want to think, this is not exactly what it is, but to give you an idea, for a spring, Jelly, what do you have? Spring equal chi x, no? Let's forget about this. Okay, I think it's going to be more confusing. So the idea I want to say is that basically the strain energy is like the stiffness of the system. But okay, so here we did the first option. That was to find the minimum of the function in function of the general displacement. We can do something similar, and this is a useful one, is to find the minimum in function of the general force, which is the capital Q. And we follow the same process, so it will be partial of partial capital Q sub I of U minus summation the two Q's equal to 0. So basically it's exactly the same thing, but we're going to reverse the action of the Q. So this is going to give you partial U partial with the forces will be equal to the summation of the deformations at that location, which will give you summations of the deformations. Basically, we can replace the value for the deformation at the point, will be equal to the partial derivative of the strain energy with respect to the general force. Okay, so this is important one, so I'm going to rewrite it. So here's something very important, okay? All right, so let's say that we have, since this is AE, okay, let's say we have a wing. And let's say you have a force over here, P. Okay, let's call here this point 2 and this point here 1. Okay, so according to this, the deformation at point 2 will be equal to what? Partial of the strain energy due to bending divided by the force that is acting at point 2 because this is the force being applied at the point P. So at the point 2. Okay, now what happens if we would like to find the deformation at point 1? If we use the same thing, so 1, we have to do what? There is no force applied at Q1, no? But in order to find the force at Q1, we need to apply the force. So how can we do that? That's right. So you see, there is no force. This would be the real point. So in order, if I ask you to find the deformation at this point, what you're gonna have to do, you're gonna have to assume a virtual force being applied at that point. And you will do other calculations, and then you will assume that force equal to 0. But basically, what I want to say over here is that in order to find the deformation at one point, you need to have one force applied at the same point. Correct. So that's what I was trying to say before, like the spring. In order to find the deformation at the spring, you have to have the force applied at the spring, no? Yes? Okay, that's what I was trying to say. But basically, this is important. You cannot find the deformation here by now taking the derivative with respect to P, because P is not being applied at point 1, no? That's will only work if it's applied at point 2. All right, so let's do one example. Obviously, just using the simplest form for the strain energy, that will be the axial. All right, so first I give the general expression. So energy method. For trusses. And I think that's where I think Professor Radosta has a problem that is like about 20 pages. So I was like, I'm not going to use that one as an example, okay? I think it's crazy. Anyway, so let's do this one, okay? So remember, trusses structures have which form? Okay, I mean, let's say I do the simplest one, but basically you can have this would be the ideal form, but let's say you can got one member or two members, no? Okay, and whatever, let's say I'll put a force over here, P. All right, so this will be a general truss construction. What is the assumption that is made when you solve truss structures? What do we say about each one of the members? Sometimes they call it two force members. Personally, I call them one force member, because basically what I want you to think about is that they can only have the force in the axial direction, no? So if the force is only in the axial direction, you have two choices. That's what they call them as well, two force members. What are the two choices? They are either in tension, or they are either in compression. Okay, all right. So we have said that the strain energy, so what will be the internal energy for something that is only subjected to axial, let's say here axial, is equal to what? Is equal to 1/2 exponential of P squared over EA. Let's say I call dx or dx, but the dx, let's put dx, doesn't matter. And we also define that the work done by the external forces, in this case, P will be equal to Q, but it will be equal to minus the summation of the Q sub I, Q sub I, uppercase Q, lowercase q. Okay, so let's say to determine the deformation, not the force, what is the equation that we just derived? We say that Q sub I needed to be equal to what? Partial U with respect to the Q sub I, no? Yeah. So this will give you what? I'm not going to do anything. This would be the partial Q sub I of what? Of the 1/2 integral P squared over EA dx. Okay, if I need to give some more information, just let me know. So Q sub I. If I take the derivative now of this, so remember, let's say if I here, let's say we want to find the location at this point here where P is applied, then Q sub I will be equal to P, no? Yeah. So when you take the derivative of P squared will be 2P, 2P dP. So this will become what? This will become the 1/2 will disappear, will become integral of P over EA partial P partial Q sub I dx. Okay, maybe let me do this. Maybe this should help. Okay. All right, so now in most cases, which is going to be in this class, trusses are made of constant cross section. So basically A equal to constant members. So that basically I can rewrite this expression here. Oh, sorry. P over EA times partial P partial Q sub I dx, and they can have different length. I mean, they can have the different length, but this will be equal. We can replace the integral sign by the summation signs of PL divided by EA partial P partial Q sub I, if you want, L sub I to N. So maybe by now you're a little bit confused. Let's just do an example very quick. Everything will become more clear, okay? Okay, so the same thing over here, all right? You can have statically determined problems or statically indeterminate. So this problem over here, would this one be statically determined or indeterminate? Indeterminate, because I put members over here, no? If I remove these two members, then it becomes statically determinate, no? If I only put one, it becomes statically indeterminate, all right? All right, so let's do one problem. All right, so basically here we're gonna go. So example, and again, all these problems require a good amount of work. It's not complicated, but it's require amount of work. Okay. So basically here we're gonna have a simple truss. So let's see. All right, so here this will be P at point A. This will be point B. And this will be point C over here, where there's a force applied at point B. F equal to 100 kilonewtons. And obviously, will this structure be stable? No, because if this is free to rotate, this will just fall down, no? Okay, to be in static equilibrium. But in order not to complicate the problem, the top one is not going to be a member or a truss member, it's just going to be a cable. Okay, that reason is why. Anyone? Is related to what we just discussed. How do you define statically indeterminate? Is that if you cannot solve it, but just using summation of force equal to 0, summation of moments equal to 0, no? Okay, so in a 2D problem, what is the maximum number of unknowns you can have? 3. So in this case, will be AX, AY, and it will be just one AX over here at the one of the cable that will be point D, no? If I put a member over here, then you will have what? AX, AY, DX, DY, no? And it will become statically indeterminate, no? So for the first example, let's do it statically determinate. All right, so each truss has a cross-sectional area of 400 millimeters squared. So this is each one of the trusses. And the cable has, and all the members have a modulus of elasticity of 200 gigapascals. Okay, the question here is to determine the vertical deformation at point C. So here comes the problem, okay? That's what is the tedious part about this method. But that's what they do again in all the final elements and other stuff, but they do it for you. So, okay, so first thing, what do we say about this problem? Is that it's statically determinate, no? Okay. All right. Second, we need to find the deformation at point C. Okay. Is it a force being applied at point C? No. So what do we need to do? We assume a force, so apply, and here we have different terms. So some people call it a virtual force, a dummy force. How do you want to call it? Apply a virtual force or dummy force, or let's put both of them. Dummy force. Let's call it Q, no? At point C. All right? Because why? Why do we have to do that? It's because we just say over here that if we want to be able to use Castigliano's theorem, a force needs to be applied at the location where we want to find the deformation. Yes? I want to say that again, okay? You need to apply a force at the location where you want to find the deformation. Even if there is no force, you need to apply one. Okay? You do all the calculation with that force, and then at the end, what you're going to do, you're going to say that force is equal to 0. But you need to keep it in all your calculations all the way to the end. Okay? All right. So here we go. So really, what does that mean? Is that our problem becomes what? So again, first thing, like always on the procedure, we need to do a figure. Okay, so if I do here the figure, let's see, what are we gonna have? We're gonna have an AY reaction, AX reaction. We're gonna have the force F. We're gonna have, let's not forget it, the mutual force Q at point C. Maybe I need to put ABC. The force at point Q. And then we're gonna have over here on the cable, we're just gonna have one reaction because it's one cable, no? All right. And remember, this is 2 meters. This is 2 meters. This is 2 meters. So that makes it a similar triangle. So all this angle will be what? 45, 45. So that's it. That's all. So like always, first step, you need to do a figure. So step one, like always, free body diagram. Step two, sometimes you don't have to do this, but let's follow. In most cases, you don't have to do it, but we're going to do it because if you want to find everything, you have to find the reactants. So in order to find the reactions, okay, what would be the easiest thing to do? First, we need to do what to find the reactions? Apply summation of forces and summation of moments. In order to save a little bit of time, I'm going to do it a bit faster. I'm first going to apply the moment equation. When you apply moments, you always need to specify about which point. So we're going to take moments about point A. So we take moments about point A, and we know this should be equal to 0. What are we going to have? So F is equal to what? 100, no? But with that one, will the 100 produce a positive or negative moment? Okay, so it will be minus 100. What will be the arm? 4. Okay. Then what will be the moment created by Q? It will be negative as well, and the other will be 2. And then what else will be producing a moment? B, and that one this time will be positive or negative. Okay, plus dx times 2. Okay. And this must be equal to 0. So the idea over here is that you need to solve for the unknowns. Okay. We don't know Q, but Q we know at the end is going to be equal to 0. So what is the only unknown over here? The reaction dx, no? We are solving for the reaction. So this will give you that dx will be equal. So you see 400. Now you divide everything by 2. We're going to find dx equal to 200 plus Q. Okay, this is statics, okay? Then we do summation of forces, let's say on the x equal to 0. So this will give you what? Ax minus dx and that's it, no? Equal to 0. So this will give you Ax equal to 200 plus Q. Okay, and finally, the last reaction, we'll find it by doing summation of forces on the y. which will give us what? If you look at the figure, that will give you just AY minus 100 minus Q equal to 0, which will give that AY will be equal to what? 100 plus Q. Okay, so we found the value of the reactions in function of Q. Okay? All right. Now, what do we need to do? We need to do the find forces on each truss member. Okay, so in order to do that, we're going to use the method of joints. So what is the method of joints? So let's see, we look here at point A. What are the forces being applied at point A? AX, AY? No? The force of the member AC and the force of the member AB, no? Okay, so let's start by AX. What is AX that we just calculated? Okay, we put it, so it's 200 and it was to the right. 200 plus Q. What is AY? Is, yeah, it's right on top, so 100 plus Q. And now, what I like to do is I like to take positive on the, I like to assume now just the, on the axial direction. So let's say this will be equal here to P AB. And this will be here P AC. And what we know about the angle is 45 degrees, no? Any question about the figure? So basically what we have here, we know cos 45 equal to sine 45 equal to square root of 2 over 2. But I mean, you don't have to use this one if you don't want. And this is really, if you multiply top and bottom by square root of 2, you get 1 over square root of 2, okay? Okay, so let's first do over here to save some time. I'll give you the right order. Let's do summation of forces on the y direction first. What are you going to get? We do y direction because that way you can get right away the expression for PAC, no? You see? Because PAB has no component on the y, no? Okay, so we do first the y. This is going to give you what? 100 plus Q minus what? Minus PAC sine 45 equal to 0, no? All right, so this will give us what? So we know this will be equal to whatever we want to use. So let's say 1 over square root of 2, let's say. Okay. So this will give us what? So, I mean, let's not rush over here. We give us 100 plus Q minus PAC divided by square root of 2 equal to 0. So this is going to give that PAC is equal to what? Square root of 2 of 100 plus Q. So pay attention here. We are finding, what are we doing? We are finding everything in function of that dummy virtual force Q, no? You find the reactions Q. All right, we have dx Q, AX Q, no? They are all in function of the virtual force or dummy force. Okay, so now that we have PAC, we can do what? We can do the summation of forces on the X direction. And then I will be able to find an expression for PAB. So we do the summation on the X, what are we going to get? 200 plus Q minus PAB minus PAC cosine 45 equal to 0. Okay? And we can say cosine 45 is 1 over square root of 2. So let's see, this is going to give what? 200 plus Q minus PAB minus, we know what PAC is. Now we divide by square root of 2, so this should be equal to what? Minus 100 plus Q, no? Yes? Okay, you want me to put the square root of 2, so it will be square root of 2 over here, and this will be 1 over square root of 2, no? But it will cancel out. So this will be equal to 0, so this will give you that PAB will be equal to what? 200 plus Q minus 100 minus Q. So this one, we find a constant value, PAB will be equal to 100. Okay, so let's say this was for joint A. Now, what we're going to do, we're going to do the same thing. We're going to move to joint B, no? Okay, let's go to joint B. All right, so we have our point B over here. Similarly, our point B here is subjected to 100 kilonewtons down. Now, from the previous page, we know that PAB, all right, is equal to 100, no? Okay, and this one was applied in tension. Okay, so that one is, so that means that now we need to reverse, no? Action reaction for PAB. So this will mean for PAC, sorry. So what now? PAB. So now this will become what? This is PAB equal to 100, no? Yeah. Action reaction. And then what are we going to have over here? We do the same thing as the other one. We're going to have here PBC or PCB, whatever you want. And the angle will be 45 again. So now we are lucky, we can use either one to find PBC. Let's do summation of forces on the X, because only one unknown. What will be the equation? 100 minus PBC cosine 45 equal to 0. We know cosine 45 can be replaced by 1 over square root of 3. So we're going to get what? Okay, so 100 minus PBC divided by square root of 2 equal to 0, which is going to give us that PBC is equal to, wait, what did I do here? So I did a mistake. This should be a plus here. It's positive and positive. So positive, positive. PBC equal to minus 100 square root of 2. Okay, finally, we move to joint C, which is the one on top. So let's see, what do we have at point C? We have our virtual force Q. We had over here PBC, you see is going. So we find okay, so we have PBC going actually on this direction, action reaction here. We have over here P AC that we had before. Then I'm going to put values now, okay? And then we have here the force. Let's see what is and then we're going to over here the force. Let's call it PCD, okay? This is one of the cable. Okay, but let's see. PBC, we know is equal to minus 100 square root of 2. So really should be pointing on the other direction, no? But let's try not to use that one then. PAC, we found that one to be equal to what? Square root of 2 times 100 plus Q. And okay. So here what we need to find PCD, no? So in order to find PCD, what can we do? We can do summation of forces on the X, which is going to give what? PCD now we need to be careful because this one you see is negative. Can we do this maybe instead of putting the negative here? I mean, if you want to leave the negative, I don't want to change the figure now. But if that one should really be going in the opposite direction. Yep. Okay. Okay. So basically, what is the X component of this force? The X component of this force should be positive, no? Yeah, because going this way, so it will be the projection here. So it will be plus PBC magnitude, okay, magnitude over here, part magnitude times what? Sine 45 plus PAC sine 45 equal to 0. So now we substitute, this is going to give us PCD plus 100 square root of 2. This will be 1 over square root of 2, 1 over square root of 2. So times 1 over square root of 2 plus PAC will be square root of 2 times 100 plus Q times 1 over square root of 2 equal to 0. So this is going to give us that PCD will be equal to what? Okay, let me know. Rushes will be 1 So it should be minus 100 here. Minus 100 minus Q. So sorry for that. So PCD will be equal to negative 200 plus Q. Okay, I mean everything is nice, not so far. Okay, so all right, here we go. So let's do a little summary of our results. So little summary over here. So let's say I'm going to put over here trust members. So we have AB, BC, AC, and CD. Here I'm going to put the value of the actual force P on each member. So what do we find for AB? We have here PCD. So let's start maybe by that one. PCD I have minus $200 plus Q. PBC, we have what? Minus 100 square root of 2. I'll go backwards on my notes. PAB, 100, and PAC, square root of 2 times 100 plus Q. Okay, so here I'm going to do, all right, so leave some space over here, okay? I'm going to add some stuff over here. So now I'm going to put over here, recalling the expression to determine the vertical deformation. So what was that equation? Q sub I needed to be equal to partial of U with respect to a partial force at I, no? So in our case, and we said that this was equal to the summation basically of the PL sub I over EA partial P sub I over the partial Q. Okay? So basically what we need to do is that calculation. So let's try to be a little bit smart over here. So we have the value P. Okay? E, we have it, was given to us, was what? 200 gigapascals, and A is the cross-section area of each member that we say was equal to, it was 400. Okay? Basically that was here on this page. We have E, A, okay? Now the length of each member, we can find it. Okay, we're going to do it next. But the other term is partial P with respect to Q. So what will be here, the partial P with respect to the virtual force. So if we do the first member, what are we going to get? 0, no? What will be the second one? 0. What will be the third one? Square root of 2. And what will be the last one? -1. Okay, now let's see what will be the length of each one of the members. So some of them are easier than other ones, but what will be AB? 4. Okay, that one is not be that important because it's going to be multiplied by 0. What will be BC? So BC could be equal to what? Will be equal to A squared plus B squared, no? So we could say will be equal to what? I know I can simplify this, but let's say to make it simple, square root of 8. What about AC? Same thing. And CD? 2. Okay. So we're almost there. Okay, so obviously here now, let's say if I apply this the above equation, our point I will be our point C. So now at point C, do we have a force being applied? Yes, we call it Q, no? So if you want, you can even call this one C over here if you want. That's fine. Call it I, but just because I made it general here, and this one you can eliminate the I. Should not matter. So Q sub C should be equal to what? We need to do the summation for each one of the members. So all the members are made of the same material and have the same cross section. So let's say I can factor out by 1 over EA. Now, how many members do we have? 1, 2, 3, 4, no? Okay, we know some of them are going to be 0, but it doesn't matter. So the general expression would be what? PAB, LAB, times partial of PAB with respect to Q plus PBC, LBC, partial of PBC with respect to Q plus PAC, LAC, partial of PAC, partial to Q plus PCD, LCD, partial of PCD with respect to Q. Okay? So all this stuff, to tell you truth, I expect you to do that in MATLAB, no? Okay, I've been telling you to use MATLAB, I think almost every single class. Okay, so let's see. In this problem, start simplifying. What would be partial of PAB with respect to Q? What is that term? 0. Perfect. Okay. Let's move to the next one. PBC. 0. So perfect. So now, partial of PAC with respect to Q, square root of 2, and this one will be -1, no? And we know the different lengths as well. So let's see, we could simplify this as what? We could say now that Q sub C is equal to 1 over EA of, let's see, so this one is 0. We're going to keep it as 0. This one is 0. What is PAC? Square root of 2. 100 plus Q times LAC. What is LAC? Square root of 8, no? Times what? Square root of 2, no? Yeah? This will be square root of 2. Okay, now we do the last one, PCD. So PCD will be minus, but this will be minus and minus will be, okay, let's put minus 200 plus Q times LCD is how much? 2, and partial of PCD over Q will be -1. So we have this. Okay, so now at this stage, we're almost done. Okay, we want to find the value. Okay, but the one that is bothering us now is the Q, correct? So what can we do with the Q? Correct. Now, like I said before, now setting the virtual slash whatever you want to call it, dummy force Q to 0. What are we going to have? We're going to have that Q sub C will be equal to what? So let's say will be 1 over EA of, so this will be 0, so will be, okay, 100. Let's not make it simplifications yet. So it will be 100 square root of 2, square root of 8, square root of 2, plus 200 times 2. So QC will be equal to what? So let's say will be equal to 1 over EA. I don't have a calculator, but this will be equal to what? 200 square root of 8 plus 400. Okay, if we do the numerical substitution, E equals to, let's say, 200 gigapascals and A equal to 400 millimeters square, which will be 410 to the negative 6 meters square. This gives you, I think, approximately Q sub C, absolutely equal to 12. I mean, I think it's 12.07 10 to the minus 3, which would be approximately equal to 12.1 millimeters. I don't know what we did this page. 7. Yeah. Okay, so since we have plenty of time, what would be a good habit to do when you do a problem? To go and check with something, no? What is the best option for us to check with? MATLAB, we need to help you do the calculation. You can check maybe with the final element, no? Okay, so since we have time, let's do it maybe. Hopefully, we're not going to run into any issues. So let's see. So I keep this one here on the field for the dimensions. And I mean, now you see, when you didn't have computers, all those calculations had to do. No? Nowadays, with final element, it's a lot easier. But you need to understand what they are doing in order to check your answers. So let's see over here. So close. Let me first file, save as share for engineering. Here we go, 418. Summer 2023. Let's go this one. I don't have one. I didn't do other models. Yeah, the other models, no? Let's say this one will be trust. Okay. Save. So let's see what can we do here. So geometry points. So we start at the bottom. Maybe we can have 0, 0, 0. That would be point A. Point B we can put here. There's no point B. Okay, so B will be 4. 0, C will be at what? At 2. 2. Okay, and C will be at 0, 2. All right. Plus this, control A to center. So let's see, geometry, curve, project, methods, and points. So we have from here, okay, to this, okay, here, okay, to this one, and then from C to A. Again, oops, what happened here? All right, and finally here to here. All right, so probably the best way here would be just to use rods. Yeah, rods, and we're not going to put any support here. I think that's the easiest option. So model, material. So this time, you see for deformation, we need to use a material. So 200 gigapascals will be to the 9. Poisson ratio 0.3. Okay. All right, we have one material property defined over here. All right. Now we're going to define a property. So right click, new. We're going to define which property a rod. Is that the easiest one? Probably. Hopefully that will not give a problem. If we do meters, this is 400 to the minus 6. All right. Cancel. Let's activate that one. And now let's say mesh control size along curve. 2, 3, 4. Come on. Let's put on each one, whatever, 8 elements. Okay, that looks reasonable. We close. Mesh geometry curves. Probably we can do select all. Okay. Rod property. Okay. Tools. Check. Coincident nodes. I don't think you should see any coincident nodes because we mesh everything at once, but I never know what the program is doing. So, all right. So, okay. Now we need to apply the boundary conditions. So let's first apply the load. So model load on the node. So let's say we have what F equal to 100. We apply it over here. Oh, it's not 100. It's really, yeah. So it's 100 kilonewtons, no? So minus 100 to the 3. Okay. Model constraint nodal. Okay, so what? You don't need to put a title. You want that? This one here. Okay, this one is just being restrained on the X and the Y, no? We can put over here X, and we can say if it gives points, we have to give more restrainment, but let's say this is just going to be restrained on the X and the Y. I mean, I'm going to do it now, and this is free to rotate about the Z, but let's maybe restrict also RX, RY. So basically, it's free to move on the Z and free to move on the Y. If you want, you can even fix this one, okay? But I think that should be enough. But we'll find out, okay? And then this one here, so about the same thing for these two here, but then we only want to restrict the X, no? Okay, so hopefully that will not give issues. I think it's going to make it move on the X, on the Y. I don't know, that might create problems. All right, we'll find out. File, rebuild. Yes, I think it's going to give an issue here. Analyze, create new. Static, okay. Analyze. Okay, looks like it did everything. All right, F5. Before. I mean, you can look at the total translation or just the TY translation, which is the one. I look first at the total translation, see what it does. Let's do a beam diagram. I don't think the contour is going to do anything on this one. Okay, total translation, we did this stuff. Okay, okay. Okay, so it looks pretty ugly now. Contour, I don't think that one will do anything. Yeah, that's what I thought. Anyway, so let's look at point C. Maybe here, let's look at F5 criteria. Okay, this is the total translation, which basically will show. So, for example, let's see this point might be moving to the right and the left. I don't like that deformation. Okay, it's fine. We'll find out right now if this looks correct or not. So we can compare. Let's look at the Y translation. Okay, okay. $1.3. So this is given what? 9.1. I don't like that result. I don't like that deformation. See? That doesn't look right here, no? Why is this 0, 0, 0, 0, and then it goes down? That's supposed to be a very simple phenomena. The same thing happens here. This one looks okay. Is the one at the bottom. Okay. Let me try to constrain a little bit more. Okay, so let's see. Model. Model, this should be good. Constraints on title. Okay, so let's see on node. We have 1, 2 nodes. So let's see, they start like this one. Edit constraints. So I think this one is this one, no? Yeah. So let's constrain also this one here. Okay.
That one should be able to, if you want to make it cable, it should be able to rotate about all axes.
That's going to give more problems, I think. Well, I understand what you're saying. So let's see. Okay. This shows the weird deformation here. What can that be? It's like it's not being attached over there. Right, let me do maybe one thing here, file, open, I'm sure I'm did it another semester. Spring,
It might be because you said the table as a member, as a person. Like, well,
yeah, but it doesn't matter because I don't think that's a problem because it will always be in tension and I'm not putting any force on the wire. Does that make sense? Once the cable is in tension, it will act as a bar. It just when they slack, no?
if you can try putting a constraint in quantity instead of that line.
I mean, that's why I'm putting the constraint here.
No, I mean quantity.
Yeah, I mean, let me see if I did it before. See, I'm sure. I mean, this one should be very simple. I'm surprised we're having issues, but let's see spring. Nastra. Then we do this one, truss. Let's see, another semester. Got a folder here called Nastra. Summer 22, no idea. Truss Castillo, maybe that one. Oh, so that one gives problems. I see now. If I did 3 models, you wanted to use beams, so let's see what is the issue here. So rods. Okay. So this one was giving issues as well. Okay, so it looks like the rods were giving problems. I'm sure now if I open the beams, it should be fine. Beams is always fine. The other ones always give some problems. You see, and this one was more accurate. Okay, let's see the boundary conditions that are used for this one. Model constraint. Funny, I use the same thing. So this looks like being the cable. I already wrote it about the Z and move on the Y. Okay, so this is the cable. Yeah, that's fine. And this should be the other one. Yeah, just what it. Okay, so boundary conditions were fine. Okay. So let's do the same thing we did over here. So this is going to create some issues. So what happened here is that the roads are giving some issues. I don't know why. If you ask me, because they're showing here. I mean, here that looks fine. That looks like the more or less is this more or less correct is here. That I don't know what is happening. Okay, so let's do one thing over here. If you want. Okay, what we can do is let's delete this. All right, and what we're going to do is delete model elements, select all. Okay, okay. Delete model nodes, select all. Okay, okay. We might have to reselect here the. Yeah, I don't know, but. Okay, let's go now to properties. I mean, it's good that we run into problems. So, element property beam. Okay, so this is, I will need your help here a little bit. So, element property type beam, shape. Let's say that they are circular, bar, Y up. So let's see the 400. will be equal to pi r squared. So what should be the radius in order to have 400? Can somebody do 400 divided by pi square root? Somebody has a calculator? Square root of 400 divided by pi.
11.28.
Okay, and this should be to the -3, I guess. Okay, is that 400? Okay, close enough, no? Now what we need to do, we do that, okay. Oh, is that correct? No. 4, no, was 3.96, yeah, you're right. 4, okay. All right, now what happens is that's a lot more tedious when you do beams because you need to mesh. I mean, you should have to do that from structures 1, no? That's what you're in structures 1, but I mean, review. So file, rebuild. I like to do the rebuild all the time. I should have, let me delete everything, and that way model, delete load set, select all. Okay, delete model, constraint set, select all. Okay, delete. You see, we have 2 nodes, model nodes, select all. Okay. All right, file, rebuild. Since we have time. Okay, so now mesh, I think, should be there. Hopefully, model, no, mesh geometry curve. Let's start at this one. So this one should be the easiest one with the beam property. Okay, it's gonna add to the direction. So the direction will be what? On the y is 1, preview. You see it's going the direction of the cross section. Okay, so it's doing good. Now, mesh geometry curve, let's do this one as well. Okay. Same thing would be y up. I hope that you know what I'm doing here. This one's going to be more complicated. Mesh geometry curve. Now, this one should be the direction. Should be perpendicular to this line, no? So how can we do that? Maybe we can do 1 and 1.
Y1 x -1.
Yes, so x91, absolutely correct. You have it right there, no? You can mesh. And now we do the same thing with this one, mesh geometry curve. So now we have what? The both negatives, no? I think we'll do it. Both positive for this one? Oh yeah, because it will go to the right. So let's see, preview, oops. 1 and 1, preview. What is doing on that one? Mesh geometry curve, but still, so 1, 1. Okay, as long as it's perpendicular in that direction, so let's see, 1, 1. Now it's going to give you this one. So I think, let's see, what would that give you? So 1, 1 is going to give you this. 2. Yeah, but 2, 1 is still going in the same direction. If you look at it, that's not going to change anything. We need perpendicular to this one, no?
1, 1 with base x at 4.
1, 1 with what?
X base at 4. So
Ah, okay. Yes, that should work. Let's see. French was doing that.
Five, 1.
Wait, the 2 I need to do to this one. Let's put here now the negative one. So what we do? No.
You have 5.
Ah, I see what you're saying. Yeah. Yeah, that one looks at 90 now, no? Yep. So it just did it right here, okay? Now tools. Check Coincident nodes, select all. Okay, preview. Okay, that should be coincident. That's good. Come on. Done. Okay. Model, load, nodal. All right, we go here. Equal to minus 100 to the 3. Okay. Model constraint nodal. Okay, so we go to this one. Basically, it's pin. So this thing should only be able to rotate about the Z. So, okay, that's what I did here. And now this one here, same thing, can rotate about the Z, but it should also be able to move on the Y, no restricted. All right, cancel. File, rebuild, yes. Save, analyze. Okay, all results. Okay, now that looks about more correct. So let's see F5. Let's just look at the Y. All right, let's look at the deformation. You see now the deformation looks correct now. Okay, and the value over there. Yeah, so basically, put on the Y is about, you probably need to put the average between these two over here now. You see, this is 12.95, 11.26 now. You need to look at this one, no? Yeah. Right, it's in that order, no? Okay, so I did not remember this one at all, but you see that rods should be the, I mean, I'm sure there's a way to make it work with rods, but it didn't work, no? Okay. Okay, so tomorrow we talk, remind me tomorrow at the beginning of the class, we talk a little bit about the exam. Is that okay? How many